In this video, we're going to talk more about the SN1 reaction mechanism, so this is a part 2 video. Let's go over our first example where we're going to talk about this substrate which has an iodine attached, which is going to react in a solution of methanol. As we talked about before, the first thing that usually happens is that the leaving group, which in this case is the iodine, is going to leave. So what you get is this situation where the secondary carbon is going to form a carbocation. However, tertiary carbons are more stable carbocations. So in this situation, I'm going to draw all the invisible hydrogens. The hydrogen here is actually going to move to this area along with its electrons, and the positive charge is going to move to the tertiary carbon. So whenever you see the leaving group be on a secondary carbon that is next to a tertiary carbon, the positive charge is always going to move to the tertiary carbon if you're going to have an SN1 reaction. So as opposed to having the carbocation on the carbon here, we're going to have it on the carbon here. So we have a more stable tertiary carbocation. The next stage is going to be the nucleophile attacking the carbocation. In this case, it's going to be CH3OH. We could do it the other way around, where we go like this, and the oxygen is going to have a partial negative charge, and it is going to attack this positive charge on the carbon. What that's going to lead to is a bond where you have oxygen attached to hydrogen and a CH3. Now, the oxygen used one of its lone pairs to form this bond. So it's only going to have one lone pair left. It had two previously. It used one of its lone pairs to form this bond, so this lone pair is left. But we're still going to have a positive charge because the nucleophile in this case was actually a neutral molecule. It was not charged. Next stage is going to be called depronation. We're going to need another nucleophile, which is going to be another OH-CH3. The partially negatively charged oxygen is going to pull the electron toward itself, and then oxygen that is attached to our carbocation is going to retain the oxygens, or retain the electrons. So at the end, what we get is OCH3 as our substituent, and that's our final product. And the reason why we don't have the dashes and wedges on this final product is because this carbon under which we have our new group, is not a chiral carbon. In order for it to be a chiral carbon, it has to be attached to four groups that are all different from one another. As you can see, it's attached to a methyl group and another methyl group, and those two are identical, so this cannot be a chiral carbon. And I have a video on chiral carbons in case you want to learn that in detail. Now let's go over one of these reactions that would happen in a ring. In this case, we have a secondary carbon, which is attached to the bromine, and then we have a quaternary or fourth degree carbon next to it. If the bromine leaves, and let's actually write the nucleophile, it's going to be water this time. If the bromine leaves, which is going to, the positive charge of the carbocation is going to move to the quaternary carbon like it did move to the tertiary carbon last time. These positive charges on carbons always want to move to higher degree carbons or more substituted carbons. So once the bromine leaves, the positive charge is immediately going to move here. However, in this case, we don't have a transfer of hydrogens, we have a transfer of methyl groups. So a methyl group is actually going to move down here, and you're going to have a positive charge on top. And then we have our nucleophile, which is the water getting involved. The oxygen from the water is going to have that partial negative charge compared to the hydrogens. It is going to have two lone pairs. It's going to be attracted to this positive charge. It's going to attack that positive charge, and then it's going to bond to that carbocation. So the result is going to be this right here, and this is still a positively charged section because the water that we added was neutral. It just had a partially negative portion to it, and since we had the positive charge on the carbon, we still have a positive charge, but now it's on the oxygen and the water molecule at large. So now we're at the stage of depronation. We're going to need another water molecule to come in and steal a hydrogen from the newly bonded water molecule. So it's going to steal the hydrogen proton, and then these electrons are going to go back to the newly bonded oxygen. So the result is going to be, I forgot the methyl group, so that's my bad. It's going to be an OH attached to that carbon, and then this right here is going to be an oxygen with 3 hydrogens attached to it. Now the question is this carbon right here going to be a chiral carbon or an achiral carbon? So one group that it has is the OH, and that's different from the methyl group. And the other two groups attached to is this and this. And those two arrows that I've drawn, those are different paths. If you go down the one that's on the bottom, you're going to hit a methyl substituent. But if you go on the one on top, you're not going to hit a methyl substituent. So those are all groups that are different from one another. There's 4 of them, so therefore this carbon is a chiral carbon. So because it's a chiral carbon, this OH can either be on a dash or a wedge. And in this case, there is no favored one. It can be either a dash or a wedge. So your final answer would be these two. You'd put a plus, and then this would be your final product. Now let's go over another example. Let's say we have this situation. And let's also say we have this situation. And we have this sort of situation. And we have this situation. Which one of these compounds are more likely to go through an SN1 reaction? So let's examine the carbons that are attached to the bromines. On this top left one, the alkyl halide is attached to a secondary carbon. This carbon is attached to two other carbons, so it's a secondary carbon. On the top right, the bromine is attached to a primary carbon because this carbon is only attached to one other carbon, so it's going to be primary. Bottom right, we have a tertiary alkyl halide because the bromine is attached to a carbon that is tertiary. In other words, the carbon is attached to three other carbons. And then in the last example, the bromine is attached to a methyl group, so the carbon isn't really attached to any other carbons. What you need to understand is that tertiary alkyl halides are more likely to go through SN1 reactions than secondary, which are more likely to go through SN1 reactions than primary, which are also more likely to go through than methyl alkyl halides. So the more substituted a carbon is, the more likely it's going to go through an SN1 reaction. These carbocations generally like tertiary carbons more than they do like secondary, primary, and methyl carbons. They really do not like methyl carbons at all. Now let's go over an example where we have a double bond. What's going to happen in this situation if we react it with water? So the bromine is going to be the leaving group. It's going to leave. And then you just have a bromine ion or bromide ion floating around. And what you're going to get, this carbon is going to become a carbocation. So at this moment, this is what you're going to have. But then, what can happen is that these electrons that are on the double bond like to be around the positive and positive carbon because the negative electrons are attracted to the positive side. So they can actually come over here, and the positive charge would move two carbons to the left in the opposite direction of the pi bond electrons. And then you can have the water coming in. It's going to attack the carbocation, which is going to then turn into oxygen with two hydrogens. And then last stage is going to be depronation, where hydrogen is going to go away. The oxygen is going to retain its electrons, and what you have is an alcohol. Now, there are technically, in this situation, two products that you could have. You could either have this version of it, or you could have this version. They look pretty much identical, but just realize that both are possible. Now, let's say we have a situation where we react this with water. If we do that, when the bromine leaves and becomes a bromide ion, we're going to have a primary carbocation on the carbon where the bromine left from. But as we know, primary carbocations are not as stable as tertiary carbocations. So a methyl group from this quaternary carbon that is next to it is going to come in and join right here. So the situation that you're going to have is going to be like that. And the positive charge will move to the now tertiary carbon, which is going to be more stable than this sort of situation. Now this thing right here happens at the same stage when bromine leaves, but I've included it as another stage just to show you how it happens. But technically, when you look at the energy diagram, it's going to be one transition state. The next thing that's going to happen is that the water is going to come in. The electrons of the water are going to attack the carbocation. Water is going to come in, and then another water molecule is going to come in and steal hydrogen. The electrons between the oxygen-hydrogen bond are going to go back to the newly bonded oxygen, and what you're going to have at the end is just an alcohol. Go ahead and rank these three examples from the best compounds to have an SN1 reaction to the worst compounds to have an SN1 reaction. So as we talked about before, when you want to determine which compounds are good candidates for an SN1 reaction, you want to look at the degree of the carbons involved. So in this case, the alkyl halide carbon, all of them are going to be secondary. This carbon is secondary here. This carbon is secondary here. So all the carbons to which the chlorines are attached to are secondary. However, let's look at the carbons around them. The carbon on the right is, for all of them, is primary. So far everything is even with these three compounds. However, if you look at the carbon to their left, you can see that here we have a quaternary carbon, here we have a tertiary carbon, and here we have a secondary carbon. It's always better to have a quaternary and a tertiary carbon next to your alkyl halide than it is to have a secondary or a primary or even a methyl. I don't even know how that wouldn't be possible. So in the case that you have a quaternary carbon next to your alkyl halide, you're going to have a methyl shift, because once the chlorine leaves, a methyl is going to have to come in and replace it. But in the case that in tertiary carbon the methyl leaves, a hydrogen, which is invisible in this structure, is going to come in and replace the chlorine. And in the case of the worst compound for an SN1 reaction, none of these two hydrogens are going to come in and replace the lost chlorine. The carbocation is going to stay at this carbon, and it's ultimately not going to be as stable as the carbocations in these two. And I forgot to mention, this is called a hydride shift because you're moving a hydrogen.